Hello everyone, welcome back to my channel. I am Jyotsna, pursuing my BE Computer Science from Sri Venkateshwara College of Engineering. Today's topic is superconductivity. Topics to be covered are Introduction to Superconductivity, Meissner's effect, BCS theory of superconductivity, and quantum tunneling. Introduction to Superconductivity. Discovery. Lord Kamerlingh once discovered the phenomenon of superconductivity in the year 1911. When he was studying the temperature dependence of resistance of mercury at very low temperature, he found that resistance of mercury decreases with temperature, with the decrease in temperature up to a particular temperature Tc is equals to 4.15 Kelvin. Below this temperature, the resistance of mercury abruptly drops to zero. Between 4.15 Kelvin and 0 Kelvin, mercury offers no resistance for flow of electric current. This phenomenon is reversible and material becomes normal once again when temperature was increased above 4.15 Kelvin. This phenomenon is called superconductivity, and material which exhibits the property is named superconductor. Definition. Thus, superconductivity is defined as the phenomenon in which resistance of certain metals, alloys, and compounds drop to zero abruptly below certain temperature is called superconductivity. Variation of resistivity with temperature. The variation of the resistivity of a superconductor, pure and impure metals, with temperature is shown below. Critical temperature. The temperature below which materials exhibit superconducting property is called critical temperature, denoted by Tc. Critical temperature Tc is different for different substances. The materials which exhibit superconducting property are called superconductors. Above critical temperature, materials is said to be in normal state and offers resistance for the flow of electric current. Below critical temperature, material is said to be in conducting state. Thus, Tc or critical temperature is also called as transition temperature. Meissner's effect. 1933. Meissner and Ochsenfeld showed that when a superconducting material is placed in a magnetic field, it allows magnetic lines of force to pass through if its temperature is above Tc or critical temperature. If the temperature is reduced below the critical temperature Tc, then it expels all the flux lines completely out of specimen and exhibits perfect diamagnetism. This is known as Meissner's effect. Since superconductor exhibits perfect diamagnetism below the critical temperature Tc, magnetic flux density inside the material is zero. The expression for magnetic flux density is given by B equals to mu naught multiplied with M plus H. Here B is magnetic flux density, M is magnetization, and H is the applied magnetic field strength. For a superconductor, B is equals to 0 at T is less than Tc. Thus we get M is equals to minus H. Thus Meissner's effect signifies the negative magnetic moment associated with superconductors. BCS theory of superconductivity. Barden, Cooper, and Schrieffer explained the phenomenon of superconductivity in the year 1957. The essence of the BCS theory is as follows. Consider an electron approaching a positive ion core and suffers attractive Coulomb interaction. Due to this attraction, ion core is set in motion and thus distorts that lattice. Let a second electron come in the way of distorted lattice. An interaction between the two occurs which lowers the energy of the second electron. The two electrons therefore interact indirectly through the lattice distortion or the phonon field, which lowers the energy of the electrons. The above interaction is interpreted as electron lattice electron interaction through phonon field. It was shown by Cooper that this attractive force becomes maximum if two electrons have opposite spin and momentum. The attractive force may exceed Coulomb's repulsive force between the two electrons below the critical temperature, which results in the formation of bond pair of electrons called Cooper pairs. Below the critical temperature, the dense clouds of Cooper pairs form a collective state, and the motion of all Cooper pairs is correlated, resulting in zero resistance of the material. Quantum tunneling. In classical mechanics, when a particle has insufficient energy, it would not be able to overcome a potential barrier. In the quantum world, the particles can often behave like waves. On encountering a barrier, a quantum wave will not end abruptly. Rather, its amplitude decreases exponentially. This drop in amplitude corresponds to a drop in the probability of finding a particle further into the barrier. If the barrier is thin enough, then the amplitude may be non-zero on the other side. This would imply that there is a finite probability that some of the particles will tunnel through the barrier. In regions where potential energy is higher than the wave's energy, the amplitude of wave decays exponentially. If the region is narrow enough, the wave can have a non-zero amplitude on the other side. Thank you for watching this video. Please like it and share it with your friends and family.